Okay, so I'll record the meeting. Fernando, whenever you can share your screen and get started.
Sure.
Perfect. Okay, so without further ado, let's get started. Try to keep it a bit shorter, so really maximum 20 minutes. I'll let you know when you're 3 minutes to that.
Sure. Thanks. Hi, everyone. My name is Fernando. I am a third-year PhD student. I'm actually almost finishing, and I'm presenting today my work on robust optimization, more applied to air traffic control, which title is Robust Aircraft Conflict Resolution under Trajectory Prediction Uncertainty. I am supervised by Dr. David Ray and Professor Travis Waller. So the core of my work is basically aircraft separation. So according to International Civil Aviation Organization, which is the organism that supervises civil aviation around the world, two aircraft are said to be in conflict if they have less than 5 nautical miles of horizontal separation and less than 1,000 feet of vertical separation. So if you have two aircrafts, and if you put those aircrafts in a center of a cylinder, each cylinder would have 2,000 feet of height and 5 nautical miles of radius. If those two cylinders are sharing any space, they will start to be in conflict. How we determine the conflict? So in this situation, each aircraft can perform 3 different maneuvers. Can change level, which is vertical maneuver, or can perform a horizontal maneuver, which are divided in angle and speed. Angle is basically how you can turn in left or right in the plane, in the same plane, or in speed, it is acceleration and deceleration of the aircraft. This is summarized in the equations of motion of the aircraft. As any moving particle, we assume in this case that we have linear motion and infinite acceleration. So we can model the motion using those simple equations over here. And based on those equations, we can create establish a separation, which is for each point in time, the position of two aircraft has to be greater than a standard given here by this variable d, the parameter d. So to impose separation between two aircraft, you have to assume that for any given time, that value separation is more than 5 nautical miles. Of course, this expression is time dependent. It has it is non-linear. So to remove the time component of this constraint, we would use some mathematical tricks to come up with a form of equation which is independent of time, which is the G equation in the bottom here. This equation still is nonlinear and non-convex, so a few extra work necessary to change that. Based on that constraint, we realized that we can break down that constraint in 4 linear constraints. And those 4 linear constraints, they are linear in terms of the decision variables, and they represent a set of 2 convex subregions in the solution space. However, to decide for each side of this, or each of those subregions we have to go, we need to utilize a disjunction to do that. And that disjunction is given by one of the normal plane to those lines. So we create a set disjunction modeled by this variable zij is a binary variable, and depending on which value this variable assumes, we are in a different side of the disjunction, basically a different side of the subregions in our space. So if you look at this plot right here, we can see that the lines R1, R2 are those 4 equations that I showed you initially, and those lines represent those 2 regions in purple represents where we have the our feasible solution, feasible region, and to to determine which side we are, we have this equation for this plane n, which is represent our disjunction. So we will determine which side of this disjunction we are. Of course, we have to remember that our decision variables are based on the maneuvers that are available for us. And when we are talking to a formulation that is on 2D, which is the focus of this work, we have speed and angle as our maneuvers. And of course, for those maneuvers, we need to have some bounds. We cannot have maneuvers as wide as we would obtain without them. So we impose a bounds on the speed and on the angle. Those bounds will be very important in the moment. So based on those four equations and based on the disjunction, we have a model to solve the problem. The model is, of course, is deterministic because all the variables are deterministic variables, but however, it has a few limitations. When you're working with a space, we have to assume that weather events are going to be a major part of that. We have wind, have rain, have storm. All these elements can influence how the aircraft speed will be determined. And also, we are talking about machines that are moving very fast, and all the communication between aircraft and a control center are done via signals and sensors, and all those elements, they are susceptible to failure. They can have a malfunction, they can provide information that is not exactly accurate. So when that happens, we're gonna have some form of randomness in our data. So we need to figure out a way to guarantee that our solution is still valid, is still optimal, is still safe, even though we might have lost some data or lost the deterministic part of our data. So for that, we have to introduce a sensitivity set to our model. So how are we going to do this? We're going to take for each of the velocity components right now, we're going to have error. In this error, we represent how how much we can assume, how much we can expect that those variables which were at the beginning were deterministic, how much they can change, how much they can vary based on some source of error, in this case, any weather or malfunction. So we determine that for each aircraft, we're going to have a epsilon I, which is basically a factor where we're going to have interference in the x and the y component. So we have independence here for each of the components, and this will cause some variation on the speed specifically of the aircraft. So the speed, which once was a deterministic variable, now becomes a random variable, and that changes how we approach the model very much. So now we have to figure out a way to sort out the same model with these random variables. Thankfully, the structure of the model is very much the same. We don't need to worry too much how to derive the constraints. So what we did, we incorporate those random variables into our equation of motion as we had before, but now the equation of motion, which was deterministic, now becomes random, and we did the same derivation that we did before, but now our four linear constraints that we had previously, they have those uncertainty sets involved on them. So before they would give us a deterministic region, now they're gonna give us a deterministic region and a robust region, uncertainty region, and they are slightly different. So if we plot one example of two aircraft, for example, we would obtain the same, in blue, we will have the same set of linear constraints. Those constraints, they don't depend on these random effects. So those lines, the blue lines over here, they'll be absolutely the same. We have our conflict region over here in red, which again doesn't depend on the velocity of the aircraft. It depends on the initial positions and the initial parameters. So those would be, the region would be absolutely the same as previous. The only thing we change is how much the velocity would range, and that we have those two different boxes. The box in the full lines in black represent the range of velocity the aircraft can assume based on the bounds that we introduced previously. And you can see that in the deterministic case, this bound is quite tight, it's strained. We don't have that much range for the speed. The speed is more contained. However, if you introduce those uncertainty sets to our velocity, we expect that that range becomes way wider, which is this dashed box. And if you have the velocity box intersecting with the conflict region, we have a conflict. In this example here, the deterministic case does not have a conflict because there is no combination of the no point inside that box which would be intersecting with this red region. However, if we change if we apply a set to our velocity, that will change, and we might be in conflict depending on which combination of velocity we go, which maneuver that would lead to a conflict. So a solution that is applicable to a deterministic case when we use the same settings, the same instance, but in a robust scenario, it might not be as easy to solve as before. And our results kind of prove that theory. So how will we address robust formulations in the literature? There are two main ways to do that. The most famous way is that given that any constraint which has uncertainty sets has to be broken down in a set of infinite constraints, each constraint should correspond to a piece of this set would have a enormous amount of constraints to handle, and the literature suggests us to go through via the dual problem. So we create a dual problem, and in that dual problem, the sensitivity sets, which are random variables for us, will become parameters. And then the constraints, instead of having a set of infinite constraints, will be a set of limited constraints, one for each random variable. However, that process is a little bit more complicated, it's involving a little more mathematics, and is not very efficient. A process proposed by Betzimer around 2004 proposed alternative way to do that. We can break up each of those random constraints into a alternative constraint where we have those same random variables as parameters, however, in a very more concise process, and that's why we applied in our formulation. So let's assume that we have our constraints. Our constraints, they are in the same way as they were. They have all the generic format. They have the deterministic part before and followed by a robust part. So to change from one set to another, we need to add 4 variables. The first variable is actually a parameter, which is going to determine how much of robustness I'm expecting in that model. It ranges from 0 to the number of decision variables that I have in my original problem. I have one variable, which I call here phi, which is corresponds to how I'm going to distribute this randomness between the constraints that I have in my model. and a third variable, which will just call row here, which will divide this randomness effect throughout the variables individually. So I have one to break down for different constraints and one to break down for each variable constraints. So it's a way to balance out how much of randomness I'm expecting of each of my variables. And an extra variable here for so I can rearrange the bounds for my decision variables so that they can account now for the random parts of that. So we did that for each of those constraints. Here I present the very generic formula, which you have the deterministic part plus the random components and all the constraints required to account for this random component. As you can see, it requires way more constraints. Initially, we have only 4 constraints to represent separation. Now we have a set of almost 13 constraints for each of those 4 originals. So instead of 4, we have now a set of 42 constraints. So it's a little bit more heavy in terms of complexity, but compare this to the dual formulation, is still quite easy to solve. So we implemented this and tried to analyze in terms of a few components. First, we have the level robustness. We can use different level robustness based on the parameter gamma, and we will explore how much gamma can change in terms of robustness and how this will impact the results. Another one was how the range of our error. It can go from 0, which is, of course, the deterministic case, until 10% of error. And we decided to change how much of the separation constraint, which was the very beginning of our initial constraint, to relax the constraint a little bit and see how this impacts in our formulation, in our results. So starting with gamma, we realized that if you have gamma equals to 0, we have, again, our deterministic model. And if the higher the value of gamma means that I am allowing more and more random effects in our model. So in this plot over here, I have the lines in black representing the nominal trajectory, and the lines in red represent the maximum of robustness I can allow, and the blue, the minimum I can allow. In this instance here, with only 5 aircrafts, the blue and the black are very close. So basically means that with minimum randomness, I can still solve very close to the nominal trajectory. But even with the red, is not too far from the original case. However, if I start to adding more conflicts and more aircrafts, for example, with 10 aircraft, I have cases, for example, the aircraft 3 over here, where the difference between the red and the blue is quite considerable. So increasing the number of randomness that are allowed causes more difficulty to solve each a simple instance, for example, with only 10 aircrafts. Running over an instance that has up to 20 aircraft, we realized that in the beginning we had a lot of errors, a lot of difficulty to solve instance with when gamma increases, we have errors, difficulty to solve instance with more than 10 aircraft. So as increased gamma, the number of instances we could solve became less, which is expected because we are allowing more randomness in a scenario which is already very dense. The same case happened when we increase the uncertainty sets. For small values of deviation, that was easy to solve, but when it becomes larger, the deviations become higher, and the number of instances that we could solve become a little bit less. And we changed the distance. Initially was easy to solve, but with more aircraft, for example, an instance with train aircraft, we realized that we had way more deviation and way more difficult to solve simple instance, and the number of instances that could be solved as the distance increased. When it becomes double, we realize we can solve way less instance, which was not a very surprising, but showed that this model, even though it's easy to solve the robustness cases, it cannot solve if the scenario is already dense. We cannot impose a higher separation constraint, which will cause infeasibility for a very large number of constraints. So to finalize, we have a model that is fully linearized and utilitarian in terms of time, and we obtain that without using the dual formulation, which is pretty good. We observe that if we increase the error, we have more difficult to solve constraints, which is also expected. However, we can solve for a very average amount of error, which is 5%, which is very standard in the literature. And with a gamma value around 2, which again is the standard case, we can solve up to 20, sometimes even 30 aircrafts less than 5 seconds, which was pretty interesting result to observe. And we observe also that if we increase the distance, we cause more visibility, but if it's not as bad as increasing the errors or the value of gamma in comparison. So this work is already finished. However, we wanted to incorporate elements, for example, for recovery, which we don't address anywhere in this project. And we wanted to apply this for different flying elements, not just aircraft, for example, drones. It could be our area where this could be applied similarly. So that's all I have for today. Thank you very much.
Thank you, Fernando. Can I ask a question?
Sure.
Yeah, sure.
Very, very good work. I really enjoyed it. I see a lot of application in not only just regular air traffic, but it could be extended to drones and drone delivery. Drones might be a little bit more complicated with the acceleration and z-axis movement, but I think that wouldn't be very difficult to extend. But anyways, my question for you is, what are the implications of changing the error values, the error threshold? I think you called it robust range or something.
Yeah.
Versus changing the minimum distance, because I assume a minimum distance works slightly differently than the error percentage. So have you thought of what is the difference if, for example, minimum distance increases versus the error value increases?
Well, the distance we normally work in the minimum, which is 5 nautical miles, and that's like the minimum value to guarantee separation, which allow us to explore the maximum capacity of the airspace. So if we increase that minimum separation, we will reducing the number of aircraft we can have on the air at the same time. So it would be better to keep the value as close to 5 as possible and just try to figure out a way to incorporate the error more. So it would be better if we could guarantee that with the minimum value for separation, we could guarantee safety for a wider range of error. That's what you asked?
Yeah, that's okay. So maybe I'm not sure whether you've done any additional numerical tests on how changing minimum distance versus changing error would affect the outcomes. But if you haven't done that, I mean, as a comment, you can think about doing that and show numerically or experimentally that, hey, this is how each of these changing in minimum distance versus changing in the error value changes the result. But good job, well done. Very proud of your work.
Yeah, thanks. We're a bit over time, so if there is a last question from the audience, we'll take that. Otherwise, students can email or colleagues can email Fernando for questions. Does anyone has a question? You can feel free to type it on the chat or just turn on your mic like Miad. No? Okay. Well, thank you, Fernando. And we'll be back next week. So have a great day. We'll share the talk later on. Thank you very much, everyone. See you next week.
Thank you, everyone.